Morning. First of all, I would like to thank Ike for inviting us all here. It's a great experience, a great host to start with, and it's a great opportunity to talk about some of the problems associated with the explosion in connectivity today. What I would like to present today is a little bit who TCI is, just a quick overview, and then some of the problems that are facing regulators around the world as this explosion of the internet and everything else is going forward. One of the aspects that sometimes gets forgotten is that the spectrum is a limited resource, and it's very hard to actually keep a control of the spectrum usage. We all like to have, I see everybody here has a connectivity, everybody's on the phone, everybody's looking at something wireless. Well, all of that requires a spectrum that is clean, that can be used all the time. And that's where TCI is actually trying to help regulators in terms of providing assistance that are used to monitor and ensure the quality of the service at the end of the day, so your experience as a user is enhanced, that you have a high quality of a service at the end of the day. With that, let me go just quickly through the agenda, a little bit about TCI, SSA, and in the middle of the presentation, I'll just address, you heard from our colleagues here, you know, wireless can make you lose a hair. I'm a clear example. It happens. For the last 40 years, there is a big transformation in the wireless industry, what is being used and how it's being used. And I'll also show some of the monitoring solutions have the same challenges as you heard from different colleagues. There are challenges in implementing. Everybody wants to have 1 gigabit Ethernet at home. Well, there are similar challenges that reflect back in the usage of the spectrum. How do I keep the spectrum clean? All of these new technologies require very careful use of the spectrum, allocation of the spectrum to make sure that the quality of service is not affected at the end of the day. And we'll give a couple of examples, and it will turn out that one of the examples of the systems is actually IAC itself has a system that has been provided at TCI, and you can see actually, I believe there is a vehicle outside that you can take a look, and it is using some of the latest technologies that are also reflecting the need of the new services coming up in the future. Again, TCI, we have been in the business for about 45 years doing spectrum monitoring and specialized frequency security and testing systems. We also can supply the systems that are essential for, let's say, airport security, communications in the different specific bands, safety and security. And we have been, SSA, located in the Silicon Valley last 45 years, Fremont, California. We are part of a company called SPX. It's a large conglomerate. It's about a $5 billion company that we have joined in 2000. The expertise that TCI brings is unique, at least I believe so. We design everything from the receivers to the software, through the antennas and everything else, trying to maximize the, if you will, the value to the user per the dollar invested. These systems are not inexpensive. They are very large capital investors, and you should be very careful to have a system that will not be obsolete in any short period of time, and it has what is called a future-proof. So you can, as you've seen, everybody was talking about 2020, there will be whole brand new technologies presented that will be providing the high-speed access to internet. All of those technologies consume more bandwidth, have a more complicated methods of delivering the information. All of that is changing very rapidly, and you would like to have your systems also being co-measured with that advance, so you do not have a system that gets obsolete, let's say, in a day or two, because the technology is changing very rapidly. That having everything in integrated system from TCI perspective, we offer that flexibility that the systems are flexible and can have a rather long lifespan. In the sense of the coverage, this map shows you we actually have systems operating currently in over 50 countries around the world. There is about a total of 730 systems around the world similar to the system that you can actually see here. So we have a long experience. We're present on all the continents and in quite a few countries. There is, as I say, over 50 countries that use TCI systems. In terms of what does drive a system design today, it's really a spectrum usage evolution that is really the factor that you have to account when you say, what does a regulator need today in terms of being able to monitor how his spectrum resources are used. Spectrum is very similar to having a gold or having an oil. It's a finite resource, and if you do not have control of it and you don't have the use of it, clearly you're not getting the best return on the spectrum usage. So spectrum regulators clearly rely on utilization data to provide efficient spectrum management. That's what all the regulators around the world do. Clearly maximizing spectrum licensing revenues, license compliance, and clearly at the end of the day, if there is a problem, you probably go back to the regulator that says, I have a license, but my spectrum is not what I expect it to be. So the regulator has a responsibility on their end to ensure that the licenses that have been issued are actually for the spectrum that is viable and usable by the licensee. And at the same time, you have the rapid expansion of wireless, where both number of transmitters and standards is just exploding. If somebody told you 10 years ago you can have a 20 megabits per second in your mobile phone, you would say not possible, right? Today that's quite possible. So there is a technology that's moving very, very rapidly, and you have to, as a regulator, follow the trends. The next slide just shows there is just explosion. Basically, as I say, I like to always say the world has gone wireless, mostly. There is a fixed service, clearly. There is a mobile service, but most of the people are using it, especially wireless part, is on the go. If you on the move, it's all basically wireless. And the wireless is, as I say, challenging. You would like to have, if you have a spectrum monitoring system, to be future-proof, so you do not have the problems as the technology is moving rather rapidly. You can cover the new technologies with the system that you have deployed. In the usage trends, clearly everybody was talking, you can go now, services are moving higher in the frequencies. When we started in the business of spectrum monitoring 25 years ago, if anybody told you go about 1 gigahertz, you would say you were really being silly. Today, everybody's pushing services way beyond 3 gigahertz and up. Signal density, signal bandwidth, today everybody's talking LTE. LTE allows 40 megahertz of the bandwidth to be used to provide your cell phone with a 20 megabits per second connectivity. All of these trends make it really difficult for the monitoring system, clearly, as the signal density. How do you know, for example, in the US, the base stations are being deployed at such rapid rate that FCC, the regulator, is actually a couple of months behind when you look at the installed database that FCC has versus what's on the air. And clearly, that is one of the potential sources of the interference that can happen. And you have to have tools to resolve the problems. The signal bandwidth, we already mentioned, if you were to consider 40 megahertz signal, even 10 years ago, it's not possible. All of that has been changed. We got used to GSM very quickly, 200 kilohertz. Everybody was happy. There was a voice, no data. The paradigm has shifted completely. Your voice is actually not a voice anymore. It is data. It sounds to you like a voice, but it's being transferred as a data across the networks. So all the networks are going really digital. There is very little analog left in the world. The next slide shows you what really is happening from the spectral monitoring perspective. You can see in the past you had a couple of big stations, you still have a broadcast stations, you still have your FM stations, your TV stations, and there are a few low power transmitters. On the right-hand side, present and the future, yes, you will still have TV services, you will still have FM broadcast, and there is many, many more low power, because what is a trend, as we said, spectrum is a limited resource, so one of the dimensions that is being controlled is the power. So all of a sudden, most of the transmitters are reducing the power. You would have to have a FM station at 50 kilowatts, you would cover a large area, but that frequency was used forever. For wireless networks to work, you have to reuse the frequencies. By reuse of the frequency, you have to control the power. So with the control of the power, now you have a real problem. How do I monitor? Lower power usually means I can't hear it everywhere. So it is just a cycle that repeats. So the technology for monitoring has to be adapted to such changes in the usage of the spectrum. One of the outcomes of that, what TCI calls is a TCI Skopje, which we would like to think it's a future-proof solution that gives regulators an opportunity to actually be prepared for the new technologies as they come online, because it has built both flexibility to adapt to new processing. Let's say new type of the format comes in, new channelization may happen, new modulations are coming on the air. If you are familiar, some of you might be, you look today, if you take a spectrum analyzer and look even here what's on the air, it's very hard to recognize manually what it is. How do I know that I gave you a license for, let's say, LTE at 10 megahertz bandwidth and you're really doing LTE at 10 megahertz bandwidth? Those questions are not easily answerable, and you do have to have a system that can help you in determining such characteristics of the signal. Spectrum monitoring challenges, as I say, every regulator is trying to deploy their spectrum monitoring systems and assets in the most effective manner. What does it really mean? You would like to have the minimum number of systems. You would like to provide a coverage of the area that you're interested in. So you have to consider many different aspects. Some of them are different emitter deployments. So you have a high density at lower power levels. You still have to monitor conditional transmitters. You have to support accurate geolocation. As you've seen on the previous slide, the density of the transmitter has been increasing steadily. If you look at some of the predictions worldwide, tenfold in the last 10 years, the density. Therefore, locating where before, if you said I can find somebody within a kilometer, was good enough because you could find, there is only one antenna. You look even here, every building might have an antenna. So which one is the transmitter that is a problem becomes a real challenge if you cannot locate with a system where the transmitter really is. So this is all playing into the challenges of wider frequency ranges. For example, you'll see the vehicle outside, it can cover to 8 gigahertz in terms of a coverage. Instantaneous wideband signals like LTE, also a challenge. All the systems operate, all of those 730 systems, they operate 24/7. So your running costs, so the total cost of ownership is very important that you have a minimum. You don't have to have extra, if you will, expenses associated with running the system at the end of the day. And differentiating between different signal formats as they come on, and you want to be prepared for any new format. As far as I know, you have a 5G is just around the corner. Everybody's talking about in the next 3 to 4 years, the 5G formats will come out, and that will be a new challenge for regulators. How do I know what is going on there? And clearly, interference with the density of the transmitter is increasing. Potential for interference is also increasing. How do you resolve any of the interference problems is one of the key abilities for the system. What TCI recommends, everybody talks about the cloud. Guess what happened to the monitoring systems? They're all in the cloud. They're all interconnected. Everybody's in the cloud because you cannot avoid. The cloud is something that cannot be avoided anymore. Clearly, you have to have ability to connect on any kind of wide area network. For example, here in Macedonia, it's a 3G is used to connect. So you can use the advances on the other end of your mobile communications to actually create your monitoring cloud, if you will, where you can go and deploy your stations to the best effect. And clearly that makes it for a very scalable solution where you can go. We have customers that start with a single vehicle, or we have customers that build a nationwide system, like example in Macedonia. So it can be any of those scenarios that can be covered with this, if you will, cloud approach. Here is just a little bit, as they would say, propaganda, typical models for different applications. As I say, some of these offerings can be tailored for specific. So we have maritime versions for if you have maritime monitoring in the large ports, you can adopt, or you can do airport monitoring where safety of life, nobody's supposed to interfere on 118 to 138 megahertz. Only aeronautical communication should happen. But it happens, you put the two FM stations together, they intermodulate, and intermodulation shows up in aeronautical band. You like to protect, clearly it's very important that those communications are not affected by any FM stations being built. Coverage, SSA, up to 8 gigahertz, there are extensions past that. And clearly, what you cannot hear, you cannot find, or you cannot listen to. So designing the antenna systems that are appropriate for all of these systems becomes very important. The typical solution is a multi-channel VF system with a wide bandwidth. You can go wide in the frequency range. One of the things is automatic calibration. As we said earlier, 24/7 operation is mandatory. You cannot have a system. People don't turn them on and off anymore. They run 24/7. Here's an example. If you've seen on the old city here, you'll see actually the sensor is on top of it. It's powered up. It's fully unmanned, and it has a 3G connectivity to the center office actually in Skopje. So the personnel can be in Skopje and can monitor any part of the Macedonia just through the cloud. So those are the types of the things. Clearly you would like the system to self-report if there is any problem, to be self-calibrating, so you do not have to send anybody to maintain and keep it running. Also multi-user, so there are multiple operators that can share the resources for different functionality. And one of the things that has been introduced in the last couple of years is, we said, the density of the transmitter is becoming much higher. Knowing their precise location becomes more and more important. That is being achieved through something that TCI calls a hybrid geolocation, where you actually combine different methods together to provide the best accuracy possible in terms of locating the transmitters. This is typically projected in one of the systems, in this example, TCI 737. That is an example of such a monitoring system that has the characteristics that we described before. So wideband, it can do both TDLA, which is one of the geolocation methods, and AOA, or it can do the hybrid. It can do advanced signal capture, and it can provide the measurements. Even LTE can be measured using a system like this. So this is the system that is designed for most demanding applications that can cover SSA, everything that is available in terms of wireless communications today and in the future as they come online. The typical example, this is how the system is composed of the antenna, processor, and a workstation. The antenna choice, this particular one is 647 that covers 20 megahertz to 8 gigahertz in one unit. Clearly, today, SSA, you would also like to have a mobile units. The size of the antenna is adapted that you can easily put it on the mobile units and not lose any performance. So that is one of the requirements when you design. If I have a mobile station, I would like to preserve all the capabilities that were present in the traditional fixed stations. And system again is controlled by a Skopje client software, and then you're just sitting somewhere in the cloud. In this particular case in Macedonia, cloud and that all the operators are in Skopje, and the system is throughout the whole country. This is just a simple graphical representation of the functionality that is available. The idea is that ease of use, ease of training, and commonality of functionality is very important, so you can have a very effective use of the system by the operators can be quickly trained and use the system. There are many different options in this, what kind of measurements, and we'll touch upon some of those when I go into details of, for example, of hybrid geolocation. Here is an example of a screen that combines quite a few functionalities. You know, from the mapping, clearly you can have the maps, Google Maps or Bing Maps. You can see the signals, you can hear the signals, you can find the location. So this particular screen is called push button DF. It hides all the complexities of the signal processing and presents a very simple display to the operators for ease of use. In the terms of the latest development, Skopje is one of the elements that is clearly evolving as the time goes to follow the developments in the wireless industry. And there are quite a few things that have been introduced lately that are driven by the wireless expansion. Some of those hybrid geolocation, as I mentioned before, combining angle of arrival and time difference of arrival. And some of you might be familiar with ITU is the governing body that actually publishes recommendations, publishes papers that explain the latest technologies as the wireless technologies are developing. The ITU is also updating everything on the spectrum monitoring. So, for example, handbook has been updated in 2011. This particular hybrid geolocation, there is a new recommendation, SM2211-1, that has been just published last April. If you open that, you will actually see some of the TCI screens and explanations, like the hybrid geolocation is probably the way to go in the future because it provides the best of both worlds, traditional direction finding and newer TDOA approach. We also added a vector spectrum analyzer function. There is another recommendation called SM1600 that says how you should go about recognizing different digital formats. That one is actually being updated as we speak, and some of the screens that I'll show here will show up in that ITU recommendation that says this is how you should go and help regulators determine what types of signals are on the air at a given time. And one of the things that is also the artifact of the explosion in wireless services, it turns out that the density is of the transmitter is increasing over time so rapidly that you also require to have a portable equipment. And there are different approaches to the portable equipment. And one of the approaches that TCI has taken said even if you have a portable equipment, It should not limit you in the functionality. A portable equipment should be equivalent of the capabilities you have in a fixed station or in a mobile station. Clearly that poses a tremendous challenge. You want the system to be portable, basically one person carrying it, and you would like to do all the other things that are possible when you have lots of power, lots of computing, big antennas, everything else. And I'll show you an example how TCI has approached to the portable equipment. Next, I have one of this new topic is hybrid geolocation. So, as I say, one of the things that you really do want at the end of the day, even if you have interference or if you want to verify the license that the people are actually transmitting from the places they claim they should be transmitting, you like to locate the transmitters. And there are many different methods, and they are actually described, as I say, this ITU report you can get, that's available online. If you go to ITU, you can download the report. It's a very nice report because it discusses different methods, not only TCIs, but it gives you basic introduction to the different geolocation. If you look at the conclusion of the report, it says a hybrid AOA-TDOA geolocation solution may offer a number of advantages over TDOA and AOA systems only. A combination of AOA-TDOA solution provides better coverage with fewer monitoring locations. That is clearly, that last statement is something that's in the interest of regulators. It says, I can get my coverage with fewer stations if I use this combination than if I do one method or the other. There are, for example, people say you can do only TDOA coverage. It turns out if you want to do TDOA only, you will end up with more stations than the actual wireless network itself. So that is probably not an optimum solution. In a hybrid geolocation, as we said before, there are different methods, and I'll show you a couple of those in the graphical so you can kind of relate to what they do. In classic angle of arrival direction finding, you have a transmitter, you have a multiple station, 3 stations, and those stations can find direction from each of the stations where the directions, like where the green sectors intersect, that's my transmitter, and where the red one intersect, that's another transmitter. So I can quickly locate. Clearly, I have to have at least 2 stations to do this. It's pretty fast, but the accuracy, further you go out, you can see that the green and the red sectors are spreading out. As they spread out, the accuracy becomes less and less. The one advantage of angle of arrival, or DF, is you can have a vehicle like you may want to see outside. You can drive a vehicle down the road, find the direction where the signal comes from, move to the next location and move to the next location, and actually from a single vehicle locate the transmitter. That is very useful. Clearly, the transmitter has to be transmitting while you're moving, but it provides ability of a single vehicle to locate the transmitter if you don't have any other resource available. TDOA, it's a very different method. It measures time difference of arrival. You always do need 3 stations, although I'll show you you can do it with only 2. That's where the hybrid comes in. So here, the location is from 3 different stations. You measure the time difference of arrival. You do very complex computations, and you come up with a dot on a map. The TDOA has one advantage. Its precision is not dependent on the distance from the transmitter. So you can get a better, more precise location. Clearly, you can only do 1 signal, and it requires a large bandwidth on the network that is interconnecting the stations. So it has the pros and cons of using it. So the next step is you do the hybrid. And in this example, I have 2 stations. One can do DF, and both stations can do TDOA. So I can get line of bearing and TDOA, and with only 2 stations, I can do now what's called a hybrid geolocation. Clearly, that concept can be expanded to more AOA and TDOA stations, and that is very similar to what's actually deployed here in Macedonia, as you'll see in a second. The deployment of a modern monitoring system is equally challenging today as is deployment. Everybody, when you say, you know, my phone doesn't work here, they didn't predict the coverage correctly. Exactly the same problem is present for deploying the spectral monitoring. So you actually do have to have tools for pre-deployment, so you don't just go and say, we'll put some stations here and we'll be okay. But with a hybrid geolocation, the prediction of the coverage becomes very, if you will, non-linear operation. You can move it just a little bit and affect tremendously the results and the accuracy that the system can provide. So, for example, in Macedonia, we provided a complete analysis for different stations. Clearly, analysis can say, put a station here, and there is no building, no power, right? You have to move it somewhere else. So you can optimize very similar processes you would have if you were to build a wireless network, how you do the coverage analysis. So that's a very important in this new and upcoming spectrum monitoring systems, that you have a full ability to do the coverage analysis before you commit putting, you know, concrete in the ground or building or renting the rooftops. It's very important to do that. For that, you have to have the terrain, data, and everything else to do the proper analysis. So TCI has developed those tools over years, and they are part of the system. So here is a typical map where you can see the terrain profile, so you can see how is the elevation, if there are any obstacles. You can put your stations with the site names, what kind of performance. Does it have just the DF or TDOA, or is it a hybrid? And once you have that, you can do what's called the hearability contours. For example, the colors on this map show, I have those 3 stations that I showed you. If the color is yellow, all 3 stations can hear a signal at 450 megahertz at 100 watts. And I can play now, I can do what if analysis in the coverage. For example, the blue color says that only 2 stations hear the signal of with these characteristics. And if that's only the case, what will happen to my TDOA? My TDOA will not work. So if the transmitter is in the area that's colored blue, my TDOA has no coverage. So those are the things that you can do with the tools like this. Clearly, you can go next step. The bar on the left is accuracy in meters. So when you display the result, where is the transmitter? You like to put a dot on the map. That dot actually has a size. You would like the dot to have a 0 meter size, to say it's really, really here. Well, that's not realistic. So the size of the dot is color coded in this example. Red means it's a really big dot. It's a kilometer big dot. And a dark blue means it's a very, very small dot. Here is a typical coverage from those 3 stations again. So you can see this. So this has both effects of propagation and the terrain and sensitivity of the system built in this coverage map. What you would like to see is one of the things we mentioned at the beginning of the presentation. The power of the transmitter today is going down because you are reusing the frequency. Therefore, the power levels are going down. So you will not find 100-watt transmitters. You probably find 10-watt transmitters. And here you can see the differences. In the same case, if you reduce the power of a transmitter by 10 dB, go from 100 watts to 10 watts, how dramatically the coverages of the system will. That also implies that you want the maximum sensitivity. You cannot have the receivers that are not super sensitive, and if you don't have that, your coverage will be diminished. Clearly diminished coverage means you'll need more stations at the end of the day. Here is just a comparison of the different methods, going from a 10-watt example. From the top left is hearability. Top right is just the DF coverage. You can see There is not that good coverage. There are a couple of stations that are active, the black dots. If you go to the TDOA only with 10 watts, which is the lower left, basically very little coverage. Yes, the hearability is the problem because you have to have 3 stations together. And then the last bottom right that says 3 sites hybrid accuracy means every station is using DF and TDOA, and you can see dramatic improvement both in accuracy and coverage, showing what the ITU report says, that the combination of 2 methods will provide you the best coverage for the number of stations. But again, you have to have a tool. It's the same as deploying the wireless network in terms of doing the coverage. So it's not just a simple thing to say, let's have 3 stations or 4 stations and let's see what happens. But with these tools, you can do the analysis before the system is actually deployed. SSA hybrid geolocation system, the goals, coverage, you have to have a precision coverage, and again, the previous slide shows the minimum number of stations is needed for the covering the given area. So it is, at the end of the day, from the regulator's perspective, it's the cost-effective solution because it requires the minimum number of stations to provide the best coverage. Here is just what I mentioned earlier. You can combine any number of systems in any shape, form, and factor. As I said, it's all done through the cloud. So, for example, bottom left, it shows 3 707s and 1 737 in a mobile. So you can imagine the mobile that is outside and sensors that are actually here in Ohrid. They all work together to provide this hybrid geolocation coverage. 707, it's a fully outdoor capable unit that can be just left out there. So it's a IP65 protected. It has a sun shield and a small antenna, very easy to install and basically any building, any place that has the vintage point that can provide the RF coverage. The specifications are similar to the other. They come in different forms, different frequency ranges, and graphically, again, what it can be done with one vehicle and one sensor. You can get angle of arrival, you can get the TDOA between the two, and you can find the precise location of the transmitter. The same thing can be done with one sensor in the middle and multiple 707 systems around. So if the signal shows up in this particular area, then the system can automatically go and trigger appropriate outside sensor to find it. Or if 2 transmitters come on, or another transmitter comes on, so that's all automatically built in the system. And clearly, it's very easy to add additional nodes if you need the coverage in the future. Clearly, also the advantage of 707 systems, because they're relatively small, they can be repositioned if you ever need, as the network that you monitor is changing. You can also change your monitoring network to adapt to the changes in the RF spectrum. Here is an example of a system. We have a TCI, the top, where it says 737 green box. That is actually TCI in Fremont, California. And there are 2 other stations. So here you can see AOA and TDOA in operation. So we have a system running at TCI all the time. And the systems are not anymore, as they call it, on a paper. They have been delivered to quite a few places. Clearly, Macedonia is one of the examples where it's a mix of fixed stations, mobile stations, and monitor and TDOA stations. We have a similar in Botswana. We have a similar in the Middle East, and we have in Asia. We have quite a large number of systems that are a mixture of 737, 707s that are using the hybrid technology. Here is an example of Macedonia system. So the control center is in Skopje, and in different places there are different set of the equipment deployed in terms of fixed stations, mobile stations, and monitoring stations. Again, everything connected through the cloud. In this case, it's a 3G cloud that is being used, and the operators are actually all in Skopje. There is 16 operator positions, and they can monitor in any part of the country from one place. Here is an example of a multiple. So here is a Skopje. You can see the disposition of the different sensors, and the yellow line is associated with the mobile that was used in this particular exercise. So this is, again, example of hybrid geolocation. Here is a precision. You can see, if I zoomed in on the map, the result was off like 150 meters in terms of locating where the transmitter is, so very precise. In the summary, hybrid geolocation, you can have a quickly deployable monitoring station, 7 of 7 is easily deployable. You get signal recording, and you get high accuracy of geolocation that is suitable, especially for an urban environment. That is one of the advantages. If you have a lot of obstacles, TDOA provides, if you will, a better performance in urban environments. Next is, okay, you were able to geolocate. We showed you how you can do the geolocation, but then you say, is that a signal really that I expect? So every regulator has a book, and it says on the frequency XYZ, signal should be GSM. And as I mentioned earlier, I look at a signal. How do I know it's GSM? I can do and buy specialized equipment and everything else, and it becomes very, very, very difficult as the signal types change all the time. And what's even more complicating is the number of changes is rapidly growing. So you'll have LTE today, tomorrow will be something else. How do I cope with that? How do I recognize those different modulations? So what TCI has done, again, following the IQ SM1600, that says, for the best analysis, you should really capture IQ data. It's just a digital representation of the signal on the air, and then go and do the analysis using this data, using different analysis tools. So if you do that, you get clearly quite a bit of the data to be collected. If you collect 20 megahertz, you get a large amount of the data. So you would end up with a network that would have requirements that would even surpass 2020. The requirements of that network would be in many, many gigabits a second. So you want to have ability to collect and record in each station. And that's what TCI has actually done. So per IQ recommendation, it says, for detailed signal analysis, the best thing is if you can record IQ data. Once you have IQ data, you can do standard signal analysis. So you can do, you can show the picture like a spectrum analyzer, so you show the spectrum. But TCI said that's okay, but the spectrum of modern signals, they all look the same. It's very hard visually to say what's the difference. So what we've done, we created something that's called user-definable signal template library, STL, where you as a user can actually define the new signal types. It says, I have a new signal type, I would like to process it. We provide the tools, and you can combine those tools to do your analysis, as I'll show you. And that library now, it's expandable. It's expandable by the regulator. So regulator, if somebody, they allow a new format to be used, new modulation to be used on the air, they can actually expand their library, and at that point, be able to tell the difference between the new signal or old signal or any other signal. So in this process, clearly you have to record the data and everything else. Once you have that, the step is very simple. You have in a Skopje, the screen that you see, we call it spectrum analyzer. So Skopje can mimic a traditional spectrum analyzer. If you look at a screen, it looks like you're running spectrum analyzer. You're really running a system in a spectrum analyzer mode. But in this mode, you can go and say this gray area is highlighted. It says, oh, that's the signal that I have given somebody a license at 879.6 megahertz to transmit GSM signal. How do I know it's a GSM signal? So looking at the signal right now could be any type of a signal. I cannot tell it's a GSM signal. So I can go and actually record the data. I can say, please record whatever is within a light gray area. Once I do that, that recording is automatically transferred to the signal analysis screen, which is basically vector signal analyzer. At this point, I have a series of tools called a spectrum, filtered amplitude, eye diagram, instantaneous phase, constellation, autocorrelation, whatever are the appropriate tools. The question is, which appropriate tools to analyze GSM signal? On the right, you can see the pull-down menu, and one of the items is GSM. And that will automatically configure my analysis setup for GSM. It will know what are the parameters that, if it's GSM, which parameters should be of what value. So when I do that, I can play my signal, and you can see there are some red markers that show up. Those markers identify if I don't see the peaks in my analysis under those markers, this signal is not GSM. So I can go very quickly and analyze all of the signals. And I have, as I say, on the pull down, this pull down is expandable by the user. The user can reprogram, you can add new modulation types or anything else. So it's a very useful and future-proof. As the new modulations come on the air, you can actually use the vector spectrum analyzer library to expand to be able to monitor new signals. So this is an example of the air. This is actually done in TCI. TCI, you can see different formats, but this channel in particular is GSM channel. Therefore, one of this spectrum vector signal analysis allows you both to confirm what you have as a regulator assigned the frequency, whether the modulation is correct, whether the user is actually doing what they're supposed to do, and as the modulation formats change in the future, you can easily add to that library without changing anything in the system. So that is an example where the development in wireless technology in terms of a transmission is being followed by the spectrum monitoring system to provide regulators the tools that are built in. In the old times, you would have to go and buy VSA analyzer from somebody that would have all of these formats pre-done, and you couldn't change anything. You were depending on the supplier to change the formats. Now the regulators are actually able to change and add the formats as they come on the air. And as the last of the developments from TCI, as I say, it's a TCI model 733, which is a portable monitoring system. As I mentioned earlier, the idea here is to provide regulators as the networks are expanding very quickly, and they might not have an opportunity even to put a 707 somewhere, but they would like to monitor particular deployments of the new technologies, to have a portable unit that provides the same capability as a fixed site or a mobile. So in the middle is the portable unit 733, has the same characteristics. It can do the same things as a fixed station or a mobile station. Basically, it has a processor, a computer, and a selection of the antennas that can be used to cover different frequency ranges. The key features, if you look through this, one of the key features is the battery operated. So the battery is actually included in the unit. It is fully standalone operable for up to 4 hours. You can recharge it, you can just plug it in a car a cigarette lighter and recharge it, or you can recharge it on the main. It has the full measurements, full bandwidth. It has the same type of the receivers that are either fixed or monitoring, so extremely high performance receivers. So there was nothing that has been shortchanged. Typically, most of the manufacturers, if you have a portable receiver, you'll see that the sensitivity, the performance, and the bandwidth is reduced because clearly it's governed by the size of the equipment. So this is example of having the same performance, so it can do both DF and TDOA. You can make a network of these portable units, same as all the other units. These are just examples of the antennas, what's inside. There is a different antennas for different ranges. You can actually get a bigger antenna if you like. Some people put a bigger antenna on the vehicle, equipment in the back of the vehicle, and when they go outside the vehicle, they take equipment and a small antenna with them and leave a bigger antenna on the vehicle. This is another antenna that goes to 8 gigahertz. This is the bigger antenna going to 8 gigahertz. Here is an installation. The rental company didn't know what we did to the vehicle, so we put the antenna on top, on the rooftop, got the cables down to the side. In the window you can see there through the plexiglass, and put equipment in the back. Or you can do this, you can have two antennas, one antenna on the roof of the vehicle, one external, and share the equipment depending how you like to use it. And that will do for you. So, thank you.